Although the natural gas industry is large and complex, its purpose is relatively simple. Your company sells a valuable product, natural gas, and your job helps ensure the accurate movement and delivery of that product. Unfortunately, natural gas has some special characteristics that can often complicate the task. For instance, gas must be contained or it will dissipate into the atmosphere. Small amounts are often sold in pressurized containers. But large volumes are moved by pipelines, and gas meters are used to measure how much gas has been moved. Most gas meters record the volume of natural gas in cubic feet. But here another complication appears because a cubic foot of gas may not always equal another cubic foot of gas. The real value of natural gas depends on the number of gas molecules contained in 1 cubic foot. Imagine these two figures as two separate cubic feet of natural gas. A is at a higher pressure than B, so more molecules are squeezed into its space. In a sense, A contains more gas. Let's look at this principle in a slightly different situation. This basketball contains air at a pressure of 2 pounds per square inch. If we increase the pressure to 8 pounds per square inch by adding more air, we have squeezed more gas into the same space. We haven't increased the size of the ball, only the pressure, and thus the amount of gas it contains. So remember, the amount of gas in a confined space will vary with the pressure of that gas. In a similar way, the temperature of the gas will affect the number of molecules in a cubic foot. Each of these balloons holds 1 cubic foot of gas at the same temperature and pressure, so they should contain the same number of gas molecules. If we heat one of the balloons, its molecules are driven farther apart, so the balloon gets bigger. In other words, its volume expands. We haven't added any gas, so both balloons still hold the same number of gas molecules, but those in B now take up more space. Thus, there are fewer molecules per cubic foot when gas is at a higher temperature than when at a lower temperature. A gas meter measures only the number of feet of gas that pass through it. The actual number of gas molecules will depend on the temperature and the pressure of the gas. Remember, the amount of gas in a confined space will vary with the temperature and pressure of the gas. Since gas temperatures and pressures do vary, most measurements are converted to a standard. In the United States, standard pressure is usually 14.73 psia, and standard temperature is 60 degrees Fahrenheit. All this may seem confusing now, but don't worry. You will receive additional training later. For now, just remember that to measure natural gas accurately, you need to know its flow rate in cubic feet, its temperature, and its pressure. Now, what does all this have to do with turbine meters? Well, a gas meter will measure the gas flow or the amount of gas that passes through it. In addition, turbine meters use equipment to make temperature and pressure measurement automatically. This meter provides a readout in cubic feet of the amount of gas that has passed through it. Now, this example registers the amount of gas in cubic feet on a circular chart covering a 7-day period. The chart will provide a record of the amount of gas flowing through the meter for any specific time during the week. A more sophisticated device measures the gas flow, time, pressure, and temperature all at one time. These figures can then be converted to a temperature and pressure standard. The measurements from a meter in a remote location can be transmitted to a computer, which can do all the necessary calculations. And this computer can keep track of a number of meters at the same time, As you can see, many types of meters are available to handle different situations. But no matter what type of meter is used, it is measuring a valuable product and must be inspected and maintained to ensure accuracy. Now let's turn our attention to how a turbine meter operates. Since it is a velocity type meter, it works somewhat like a windmill. A windmill consists of a number of blades on a rotor that turns as wind passes over the blades. The rotor turns faster as the wind increases in velocity. In fact, the rotor's speed will increase in direct proportion to the flow of air over the blades. Likewise, the rotor on a turbine meter has blades and turns in direct proportion to the force of the gas flowing over the blades. The faster the gas flow, the faster the rotor will turn. Imagine that the meter is a revolving door in the pipeline. A turbine doesn't actually look like this, but the analogy will illustrate the principle involved. As gas flows through the pipeline, it turns the turbine meter's rotor, and that movement is recorded on the register. If we increase the flow rate, more gas will move through the line, and the rotor will turn faster. If the flow rate slows down, the rotor will also slow down. All gas meters are designed to work within a specific range. And this is defined as the range of gas flow under constant pressure at which the meter will operate at a plus or minus 1% accuracy. Say a meter has a range of 5 to 20 feet per hour, or a 4-to-1 range. This means that any gas flow between 5 and 20 cubic feet per hour will be measured with the required plus or minus 1% accuracy. If the flow rate is outside of the meter's range, it may not measure within the desired degree of accuracy. And this is especially true at low flow rates. If the gas flow is above the meter's range, the meter is operating over range. Not only could inaccurate measurements result, but the rotor bearings could be seriously damaged. If you suspect that the meter has operated over range, it should be given a thorough inspection. One unique characteristic of a turbine meter is that its range will increase as the pressure of the gas flow increases. Let's return to the revolving door model. As the gas flows through the meter, it turns the rotor, which registers on the recording device. If the pressure of the gas increases, more molecules are squeezed into the same space. Therefore, more molecules pass through the meter for each turn of the rotor. In effect, the meter is measuring a greater amount of gas, so its range has been increased. Now let's see how this principle affects the operation of a meter in the field. This graph represents the ranges for a specific type of turbine meter in common use. The meter's range is represented by the line on the left, while the pressure of the gas is illustrated by the bottom line. The blue bar shows that the gas is at a pressure of 150 psi, and the meter's range is 36 to 1. In this situation, the meter will measure at plus or minus 1% accuracy any flow from over 233,000 cubic feet per hour down to about 6,000 cubic feet per hour. If the company needed to send more gas, they could increase the pressure by squeezing more gas into the pipeline. Of course, any increase in the flowing pressure will also increase the flow rate of the gas. Now, say the pressure is increased to 350 psi. A turbine meter would still measure accurately because its range would automatically increase to 60 to 1. Now, even if the pressure increases to 450 psi, the meter's range will increase to 77 to 1, and it would be able to measure flows of over 1 million cubic feet per hour. An orifice meter would require a number of different plates to cover this pressure range. Before moving on to the parts of a turbine meter and how they work, let's review what we have covered so far. First, gas must be contained somehow, or it will dissipate into the atmosphere. Second, the number of gas molecules in a cubic foot will vary with the pressure of the gas. If the gas is at a high pressure, more molecules will be squeezed into the area. Also, as the temperature of the gas changes, it will affect the number of molecules. Gas at a low temperature will have more molecules per cubic foot than gas at a higher temperature. Fourth, the turbine rotor will spin in direct proportion to the force of the gas flow. The faster the flow, the faster the rotor will spin. And fifth, all meters have a specific range of accuracy. This is the range of gas flow under constant pressure that the meter will measure with plus or minus 1% accuracy. And finally, the turbine meter will automatically adjust its range to changes in gas pressure. So we have covered some general principles of gas flow and turbine meter operations. In part 2, we will examine the parts of a turbine meter and how it operates. But before continuing, please complete the review sheet for part 1. Now that you have some background on the principles of gas flow and turbine meter operation, let's examine a meter installation. Typically, the pipeline is divided into 2 sections, so the gas flow will not be interrupted when the meter is disconnected. The bypass line may or may not have a meter unit. If it doesn't, the flow will not be measured and will have to be estimated while the meter is inoperative. In the piping, there may be a fitting that holds a strainer or filter. This strainer prevents dirt and trash from reaching the meter, since such deposits can damage or clog the rotor. If the gas flow is turbulent, the pipeline will often contain straightening vanes. They eliminate swirling cross-currents and ensure that the gas flow is perpendicular to the rotor. Usually they are permanently installed and do not have to be removed for maintenance. That brings us to the turbine meter, which consists of 2 major parts, the register and the turbine modules. The register provides a readout of the gas flow. It is located above the pipeline and is not pressurized. The turbine module consists of the rotor, the bearings, and in some cases, worm gears. Since the turbine module is sealed in the pipeline, it operates at the same pressure and temperature as the gas flow. In most models produced in the United States, the module can be serviced without removing the entire meter housing from the pipeline. The gas enters the meter and strikes a diffuser, which forces the gas flow towards the outer blades of the rotor. This action increases the velocity of the gas and provides a more accurate measurement of low flow rates. The gas flows through the blades, turning the rotor like the wind turns the blades of a windmill. Each manufacturer produces a slightly different style of rotor. Most are made of aluminum alloy or high-impact plastic. No 2 rotors can be made exactly alike, so each meter must be calibrated individually. If a new module is installed or the rotor is replaced in an existing module, the meter must be recalibrated against a known gas standard. In most cases, recalibration will be done in the shop or lab. Remember, if any major repairs or replacements are made to the rotor, the meter must be recalibrated. The rotor may be supported by several different types of bearings, depending on the manufacturer's design. The bearings may be self-lubricating or may have to be lubricated on a regular schedule. You will have to know the manufacturer's instructions for each type of meter you inspect. Lubricating the bearings cannot be overemphasized, since it is a major cause of meter failure. There are two methods of transferring the rotor movement out of the sealed pipeline. In the electromagnet design, the rotor movement is transformed into an electrical impulse by an electromagnet and a coil. This impulse is transmitted through the pressure-sealed module to the register. Since the rotor movement is changed into an electrical impulse, it can be recorded on an electronic totalizer or computer adjacent to the turbine meter, or the impulse can be transmitted miles away to a central data location. In the mechanical design, the rotor's motion is transmitted by a set of worm gears to a magnetic coupling. The magnetic coupling allows the rotor impulse to be transferred out of the sealed unit. The impulse passes to a series of intermediate gears that contain the change gears. If the temperature and pressure of the flowing gas is stable, a specific set of change gears can be installed. They will provide a readout in cubic feet adjusted to any desired standard. Finally, the rotor's movement is recorded on the register. In this case, it is a digital readout. However, many different types are available. The construction of a turbine meter is quite simple, since moving parts have been kept to a minimum. Although it is uncomplicated, it is a very specialized piece of equipment and should be kept clean and free of damage. Remember, the basic parts of a turbine meter are the diffuser, the rotor, and the bearings. These are followed on the mechanical design meter by the worm gears and the magnetic coupling. The intermediate gears that contain the change gears, and finally, the register. Now turn off the recorder and complete the questions for part 2. Since turbine meters are specialized pieces of equipment, they must be inspected and in some cases lubricated on a regular basis. The maintenance needs of meters may vary, so most companies have an inspection schedule for each meter. You will be given this information once you are in the field. The amount of time between meter inspections usually will be determined by how the individual meter is used. Meters measuring clean, dry gas will usually need less maintenance than those monitoring unprocessed production gas. Hydrocarbon liquids can wash out lubricating oil in the bearings. Slugs of liquids or hydrates can damage and completely clog the rotor. Brands and types of turbine meters will differ slightly, but in general, the field inspection should consist of 6 main procedures. They are 1. Disassembling the meter. 2. Performing a preliminary spin test. 3. Visually inspecting the meter and its components. 4. lubricating the bearing if necessary. 5. Performing a final spin test. And 6. Reassembling the meter. Meters are found in many different locations, so be sure to familiarize yourself with the layout before beginning any work. After surveying the location, shut down the line on which you will be working by closing the proper valves. A bypass line allows a continuous gas flow so that there will be no interruptions while you are dismantling the meter. You will find the rotor module enclosed in the line and at the same pressure as the gas flow, which can be extremely high. So be sure to bleed the line after you close the valves, or you might get a dangerous surprise when you unbolt the meter housing. This particular meter sends an electrical impulse to a central receiving station. After removing the top plate, check the connections and test the circuit with a voltmeter to ensure that the current is off. Then remove the register from the meter and inspect all parts for damage or wear. Next, remove the bolts holding the cover on the coupling and the change gears. Lift the plate off and examine the housing for dirt, liquid, and damaged gears. Carefully unscrew the change gears and inspect them for worn or broken teeth. The arrow is pointing to the magnetic coupling and the flange on the change gears. When the gears are in place, the coupling turns the flange, which drives the change gears. Next, carefully remove the top of the magnetic coupling. This will uncover the pin that drives the coupling. Check both the pin and the fitting. Finally, examine the gasket around the change gear housing. If everything is okay, reassemble the housing. After you are sure that the gas flow is off and the pressure in the line has been released, begin to unbolt the meter's top plate from the meter housing. When the meter's top plate is free, very carefully lift the rotor module out of the line. If the module is a large one, lifting it may require 2 people. It is very important that the rotor is not bumped or damaged in any way, or the entire module may have to be replaced. The top plate with the module should be placed on a stand in an area that is not affected by the wind, since even a slight draft will be enough to affect the test results. Next, carefully inspect the line and fitting for dirt, nicks, or anything else that might damage the rotor blades. Then perform a preliminary spin test on the rotor. This test will provide an indication of the bearing condition and the meter's accuracy. First, inspect the rotor blades for damage. Then, while holding an accurate watch, place your finger on the rotor and spin it quickly. Note the exact second that you start to spin the rotor. Next, calculate the amount of time it takes the rotor to come to a complete stop. Compare the result to the average standard spin time for that specific meter. This standard is provided by the meter company, or your company may have determined it when the meter was initially installed. If the spin test is significantly slower, say 3 or 4 seconds, it indicates an increase in friction resulting in inaccurate readings at low flow rates. Inaccurate readings may be caused by a lack of lubrication, bearing wear, or some other problem. Your company's policy may specify making field repairs, taking the rotor module into the shop, or simply replacing it with a new module. Be sure you know what to do if a spin test is below normal. After the preliminary spin test has been completed, examine the gear assembly for worn or missing teeth. The assembly is usually located directly behind the rotor. Then lubricate the gearing according to the manufacturer's or your company's instructions. Throughout the entire procedure, it is essential that you be very careful, since some of the parts are very small and can easily be dropped or mislaid. Take your time. After completing all inspections, lubrications, and repairs, a final spin test should be conducted. Lubricating the bearings will often affect the results of this test, so be sure to lube first. The final test is performed the same way as the preliminary one, but it should be repeated 3 times and the average spin time compared to the established standard for that individual meter. Be sure you know what your company's policy is concerning a meter that does not come up to the standard. Before reinstalling the module into the body, examine the body gasket and repair or replace it if necessary. Finally, reinstall the module into the line. Remember, the spin test should be the last step before reassembling the meter. Open the valve very slowly when pressuring up the meter. It is important that you take special precautions during this step. If the pressure increases too fast, the rotor may overspeed and be permanently damaged. Have all the necessary tools available and know what you are going to do before you start. The basic procedures for testing a turbine meter are the same even if the meter is in a different type of location. First, familiarize yourself with the layout. This installation has 2 parallel lines, each having a meter. The gas flow is diverted through one line, while the second line is shut down for inspection. During normal operations, both lines would be open. Close the valves and relieve the pressure in the line. This is a large meter. You'll find it is more convenient to remove it from the line in one piece. A special stand is used to hold the meter while the inspection is performed. Some companies will prefer that the preliminary spin test be conducted before the gearing is removed. If the spin time is below the standard, it may be due to worn bearings or a problem in the gear train. You can isolate the cause by doing a spin test after you remove each major part of the unit until the spin time comes up to the standard. For this example, let's assume the spin time was slow. Remove the register and perform another spin test. If the spin time is still slow, remove and inspect the intermediate gears and conduct another spin test. Continue this procedure until you have isolated the problem. After you have located and repaired the problem, continue the inspection of the bearings and worm gears. Don't forget to lubricate them according to the manufacturer's instructions. Finally, perform the final spin test and record the spin time. Remember to use the average from 3 spins as the test result. If the spin time corresponds to the standard for that meter, reassemble the meter. Always check the line housing for dirt or liquid and replace the gasket if it is damaged. Reinstall the module into the body and pressure up the meter run very slowly to avoid damage to the rotor. In some cases, there will be other equipment that will have to be inspected at the same location. This is a portable pressure tester. Its readings are compared to the regular pressure readouts to make sure that the instrument is operating accurately. Also, a special connection may be in the pipeline for inserting a thermometer. This provides a check of the accuracy of the temperature recorder. If any special tests are to be conducted on the location, be sure you know what and how before you leave for the job. Take all the necessary tools and specialized equipment you may need. Congratulations! Now you have a general background in turbine meters. You will continue training on the specific types of meters, equipment, and locations at which you will be working. But before you feel too confident, complete the review questions for Section 3.